SpaceX just shocked the scientific community, and it's not another Starship test flight. A groundbreaking proposal has surfaced, retrofitting Starship with nuclear propulsion to slash Mars travel time from 9 months down to just 52 days. This isn't science fiction. We've been testing nuclear rocket engines since the 1970s, and engineers now have detailed plans showing exactly how to bolt atomic power onto Elon's Mars ship. But here's the problem. Deadly radiation, untested methane nuclear reactors, and handling challenges that make reusability nearly impossible. Let's dive right in. And the implications could fundamentally change how here's what nobody's telling you about this nuclear Starship concept. It's not just theoretically possible, it's been mapped out down to the last kilogram of radiation shielding. We approach Mars colonization. Let's start with the problem we're actually facing. Every Mars mission designed today slams into the same physics barrier. Chemical rockets, even SpaceX's cutting-edge Raptors, burning liquid hydrogen and oxygen, cap out at around 465 seconds of specific impulse. In practical terms, that means 90% of your spacecraft mass is just fuel. You're essentially building a massive flying gas tank with a tiny crew capsule bolted on top. Even with Starship's groundbreaking design, reaching Mars requires roughly 12 orbital refueling missions. After all that complexity, astronauts still face 6 to 9 months of exposure to cosmic radiation, bone density loss, and psychological stress. Elon keeps promising faster trips, but chemical propulsion has hit its theoretical ceiling. The laws of chemistry won't bend. That's exactly why engineers are revisiting a technology we abandoned 50 years ago. Nuclear thermal rockets aren't science fiction. They're proven technology we stopped developing for political reasons, not technical ones. Back in the 1970s, NASA successfully tested nuclear rocket engines that generated gigawatts of power. These engines deliver 3 times the efficiency of chemical propulsion while maintaining similar thrust levels. The specific impulse jumps from 465 seconds to over 900 seconds, which translates directly into carrying far less propellant for the same mission. The real breakthrough in this new proposal? You don't need to design a spacecraft from scratch. Engineers have detailed exactly how to retrofit the Starship we're already building. The basic structure stays intact. Same 50-meter stainless steel body, same aerodynamic flaps, same landing system, same super heavy booster. Instead of massive liquid oxygen tanks feeding Raptor engines, you install compact nuclear thermal reactors that superheat methane propellant to temperatures chemical combustion can't reach. The exhaust velocity more than doubles, and suddenly you're playing a completely different game. 3 nuclear engines producing 7,829 kilonewtons of thrust, weighing just 24 tons, including radiation shielding. The tank space previously occupied by liquid oxygen, now filled with 617 tons of methane propellant. You've dramatically increased usable fuel capacity without changing tank dimensions. The performance metrics tell the real story. Total delta V increases to 11,153 meters per second, higher than the chemical configuration. You're not sacrificing capability for this nuclear upgrade, you're gaining it. With slightly uprated engines at 9,128 kilonewtons, adding just 5 tons of mass, payload capacity jumps from 100 tons to 245 tons. That means reducing orbital refueling missions from 12 down to 3. Think about what that means economically. Every eliminated refueling flight saves tens of millions of dollars and weeks of mission time. The cost structure of Mars colonization just shifted by an order of magnitude. This is where most people assume the concept falls apart. Nuclear reactor, human crew, confined spacecraft sounds like a disaster waiting to happen, right? The engineering solution is more elegant than you'd expect. A fission reactor emits 3 types of radiation: fission fragments, gamma rays, and neutrons. Each requires different shielding approaches. Fission fragments are heavy particles, easily stopped by the reactor housing itself. Gamma rays need dense materials. Tungsten works perfectly because it won't melt under engine heat like lead would. Neutrons require hydrogen-rich materials to absorb them effectively. The shielding design uses a 2-layer system. 2 centimeters of tungsten backed by 2 centimeters of boron carbide ceramic, totaling about 345 kilograms per engine. That sounds heavy until you factor in the natural shielding already present. Starship carries 30-plus tons of methane for landing reserves, and methane happens to be excellent at absorbing neutrons. For most of the journey, you've got several meters of propellant providing passive protection. Distance provides another critical layer of defense. The nuclear engines mount 25 meters from the crew compartment. Since radiation spreads equally in all directions, this separation means the crew only receives about 1/625th of the total radiation output by the time it reaches them. The reactor's beryllium reflector contains additional radiation before it even escapes the engine housing. There's one more clever detail. Starship's large aerodynamic flaps could potentially scatter radiation toward the crew during burns. The solution? Retract them during nuclear engine operation. No redesign needed, just operational procedure using existing hardware. Every previous nuclear rocket proposal used liquid hydrogen as propellant because it delivers the highest specific impulse. But hydrogen creates massive practical problems. It's extremely low density, requiring enormous tanks. It constantly boils off, demanding complex insulation and active cooling systems. Storage and handling become engineering nightmares. This proposal breaks from convention by using methane instead. Methane is 4 times denser than hydrogen, allowing you to carry far more propellant in the same tank volume. It doesn't boil off as aggressively. Most importantly, Starship already uses methane for its chemical raptors, so you're leveraging existing infrastructure, existing tanks, existing ground systems, existing supply chains. Yes, methane-fueled nuclear engines sacrifice some theoretical efficiency compared to hydrogen variants, but the density advantage more than compensates. You end up with superior overall performance because you can actually carry enough propellant to accomplish ambitious missions. It's the difference between theoretical optimization and practical engineering. Let's talk about what this actually enables. Standard Mars transit time drops to 88 days. Under optimal planetary alignment, that shrinks further to just 52 days. You've cut the journey by 75% compared to chemical propulsion. The implications cascade from there. Radiation exposure during transit, massively reduced. Bone density loss from microgravity, minimized. Psychological stress from isolation, far more manageable when you're talking about 2 months instead of 9. The shortened travel time also extends your launch windows. Mars and Earth align favorably only every 26 months with chemical propulsion, creating narrow mission windows. Nuclear propulsion's higher delta V opens up flexibility. You could potentially complete round trips before planetary positions drift too far apart, enabling crew rotation and faster infrastructure build-out. There's also a middle ground operational mode worth understanding. A standard orbital mission requiring 9,200 meters per second of delta V only needs 323 tons of methane, not the full 617-ton capacity. You could partially fuel the tanks to reduce launch mass and costs while still delivering performance that crushes any chemical system. This flexibility makes the vehicle adaptable to various mission profiles without redesign. Every revolutionary technology has catches, and intellectual honesty requires acknowledging them clearly. First, methane-fueled nuclear thermal rockets remain largely untested. We have substantial research on hydrogen-based systems from the 1970s, but methane represents newer territory. The combustion chemistry differs, heat transfer characteristics change, and unknown challenges will surface during actual development in testing. Second, radioactivity doesn't disappear when you shut down the engine. After firing, the reactor core remains dangerously radioactive for days or weeks. This fundamentally complicates SpaceX's reusability model. You can't simply land, tow the vehicle back to the pad, and launch again like current Starship prototypes. Ground operations require specialized remote handling equipment, radiation-hardened facilities, and extended cooling periods. Every landing becomes a complex hazmat procedure rather than a routine turnaround. Third, operating nuclear spacecraft near other vehicles creates serious constraints. You can't dock with the International Space Station while your engines are still hot. Close proximity operations with other spacecraft become radiation hazards. For long-duration Mars missions, decay time during transit makes this manageable. But for frequent Earth orbit operations, it's a significant limitation. Fourth, Mars surface operations face new challenges. A nuclear starship requires nearly 3 times more methane than chemical variants, 617 tons versus approximately 200 tons. While you're no longer producing oxygen, the methane production infrastructure must scale dramatically. Building a Sabatier reactor and mining operation capable of generating 617 tons of fuel represents a far heavier industrial investment than systems producing 200 tons. Your Mars-based complexity just multiplied. If this concept shows such promise, why hasn't SpaceX announced it as their roadmap? The answer involves multiple factors. Political and regulatory barriers loom large. Launching nuclear material aboard rockets, even dormant reactors that only activate in orbit, faces massive approval hurdles. International treaties, public perception, environmental reviews, and safety certifications could delay development for years. One launch failure carrying nuclear components, even unactivated ones, could generate public backlash that ends your program. SpaceX's strategy likely prioritizes proving Starship with chemical propulsion first, demonstrate reliable flight, perfect reusability, establish orbital refueling, begin Mars cargo missions. Once that foundation solidifies, nuclear propulsion becomes the next evolutionary step, rather than a risky all-or-nothing bet. This staged approach reduces program risk and maintains momentum even if nuclear development hits obstacles. There's also a possibility SpaceX has been quietly studying this concept for years, waiting for the right strategic moment to reveal it. The company has history here. Raptor 3, Starship version 2, the launch tower catch system all appeared publicly when ready, not during early development. Could nuclear Starship be a capability they're developing in parallel, ready to deploy once chemical Starship matures? Strip away technical specifications for a moment and focus on the bigger picture. If nuclear Starship proves viable, Mars transitions from aspirational goal to practical destination. A 52-day journey is something people will actually sign up for. Investors will fund it, governments will partner on it. You can realistically rotate crews, build permanent infrastructure, and establish genuine settlement rather than symbolic flags and footprints missions. The implications extend beyond Mars. Asteroid mining becomes economically viable when transit times drop from years to months. Ocean worlds like Europa and Enceladus, which may harbor life, suddenly fit within human mission durations rather than requiring generation ships. Deep solar system exploration to Neptune, Pluto, and beyond becomes achievable within individual career spans. We're not discussing incremental improvement to existing rockets. This represents unlocking the entire solar system for human exploration on timeframes that make practical sense. That's the genuine shock value here, and why scientists are paying attention to this proposal. Here's the bottom line. The biggest barrier to Mars isn't technology, it's time. 9 months in space breaks bodies and budgets. Nuclear propulsion cuts that to under 2 months, and the engineering to make it happen exists right now. This is exactly why SpaceX's silence on nuclear Starship is so telling. They're not ignoring it. They're being strategic. Prove chemical Starship works first, establish refueling infrastructure, then introduce nuclear as the next evolution. It's smart, staged development that reduces risk while maximizing long-term capability. And this is just the beginning. NASA's actively funding nuclear propulsion through Project Draco. Multiple aerospace contractors are testing reactor designs. The regulatory landscape is shifting as governments realize chemical rockets won't efficiently take us beyond Mars. We're likely 5 to 10 years from seeing nuclear spacecraft in operation, and Starship's design makes it the perfect platform. What this ultimately means, we're not just talking about faster Mars trips. We're talking about unlocking Europa's subsurface ocean, Titan's methane seas, and asteroid mining that could transform Earth's economy, all within our lifetimes. Nuclear propulsion is the gateway that turns science fiction into engineering projects. Here's my question for you. Should SpaceX go nuclear now or perfect chemical Starship first? Drop your thoughts in the comments. I read every single one. If you found this analysis valuable, hit that like button. Subscribe to Space Hub for deep dives into space breakthroughs that actually matter. and turn on notifications so you don't miss our next breakdown. We're tracking every major development in the new space race. This is Space Hub, where we cut through the hype and show you what's really happening in space exploration. The future's being built right now. Let's watch it unfold together. Elon Musk reveals Starship landing trick. Never done before. SpaceX just got FAA approval documents for the most ambitious rocket recovery ever attempted. For the first time, Starship will return directly to its launch site in Texas. Not the ocean, not a downrange pad. The flight path, screaming across the Pacific at Mach 25, cutting through Mexican airspace where 200 aircraft fly per hour. We're talking 4,000 potential flight disruptions annually. This return-to-launch site maneuver has never been done with a vehicle this massive. The technical challenge is brutal. Survive 1,400 degrees Celsius re-entry, nail precision landing burns, and get caught by Mechazilla's arms. Flight 11 is next. Let's dive right in. The FAA documents lay out exactly how this unprecedented maneuver will work, and the details are stunning. After Starship launches from Starbase and completes its orbital mission, the upper stage begins its return journey over the Northeast Pacific Ocean, just north of Hawaii. This is where the complexity begins. At orbital velocity, Starship is traveling at approximately 27,000 kilometers per hour. That's roughly 25 times the speed of sound. The vehicle must survive the furnace of re-entry while following a precise flight corridor that cuts across the Pacific, passes directly over northern Mexico, and terminates back at the launch site in Texas. This isn't just a technical challenge. The flight path intersects with some of the busiest commercial airspace on Earth. According to the FAA assessment, up to 200 aircraft transit this corridor every single hour. With SpaceX planning 22 Starship launches annually, between 3,000 and 4,000 commercial flights could face delays or rerouting each year.